Okay, right. So example chaotic maps that we can analyze. And this will be, again, sort of organized in terms of straightforward examples that we can say a lot about, and then becoming sort of more and more realistic, and ending up with the quadratic logistic map, about which we actually understand a good deal, but not everything, even still. Okay, so the first example, it's called the shift map, and I'll explain why it's called the shift map in just a second. Very simple map. Let me just explain it graphically. So again, here's my unit interval, one-dimensional state space across the one-dimensional state space. Again, and the benefit of looking at one-dimensional maps is I can actually graph the right-hand side, which I've done in green here, and also whenever I put down a one-dimensional map, I always draw the diagonal. It's very helpful to get oriented. So this is simple. The next value is just 2 times the previous value, mod 1. Just put it back on the interval, right? If x0 was 3/4, I'm going to get 1.5. Subtract off the 1, that maps it back to half. Okay, so that's what I'm showing here. This would be 2x, but then mod 1 makes it appear to have this other piece to it, because I'm just modding back onto it. Right? Everything, all x values above a half get mapped to a value, an intermediate value greater than 1. I subtract off the 1 and I get this. So this is what it looks like. These 2 monotone pieces, each with slope a half. So this is, we're looking at f of x, and wherever f of x crosses the identity, we know there's a fixed point. Well, here, that's just right at the origin. That's the only place it actually crosses the identity. Now you might say, well, it crosses at 1, but when we do mod 1, we identify 0 and 1. So we think of this as being on the circle. They're essentially the same point, mod 1. We can, again, just read off the stability of this fixed point. Slope is greater than 1 here. In fact, it's 2. In fact, it's 2 everywhere. So every point has a little bit of instability around it. There's also a period 2 orbit. And if you remember the trick, what we do is, if we're looking for a period 2 orbit, we can look at fixed points of f squared. So that's what I've done here. So the green monotone pieces, these have slope 4. Okay, and I've got 4 of these, and then there's still the fixed point at the origin. That hasn't changed. But now f squared crosses at 2 points, actually 1/3 and 2/3. So we have 2 fixed points of f squared, and it turns out that this is a single period 2 orbit for f. Hops back and forth, low, high, low, high, low, high. Is it stable or unstable? Again, we just look at the slope at the 2 points. The slope is 4, much larger than 1, very unstable. In fact, you can kind of imagine as I look at f cubed and f to the 4th, well, I'm going to get more and more pieces here. F cubed will have 8 pieces of the map, slope 8. F to the 4, 16 pieces, slope 16. Crossing at more and more points along the identity, therefore there are more fixed points or periodic orbits of f, but they're all very, very, very unstable because the slope about them is getting even larger. So this map has an infinite number, a countable infinity of periodic orbits, and they're all unstable. So whatever the idiots are doing, we're going to at least have some vestiges of all these periodic orbits. But they're all unstable, so they're never attracting. Now, I, again, misled you. Seems to be my habit here is misleading you. I've been saying, oh, these complicated orbit sets. You can't solve for this, write down a closed form solution for these chaotic systems. So the shift map, it's actually embedded in the dissipative Baker's map, in the horizontal coordinate. Just it's the simplest example chaotic system. But in fact, it's completely solvable. And here's the solution. There, closed form. So if I start off at x0 and I go n steps ahead, then I just am multiplying the initial point state by 2 to the n, and then mod 1 to put it back on the interval. That's pretty closed form. So what's going on here? Why? It's not complicated at all. I mean, you look at this, closed form expression. Right? What do I mean by closed form expression? I plug in an initial condition, and for all times, I can get out the state at some time later. So what's going on here? Well, it's a little bit an issue of interpretation. So now I want you to think of when I specify the initial point on the interval, say a third or 1 over pi or something like that, think about its binary expansion. So these are numbers on the interval, therefore it's going to be 0 dot something, a fractional part. So if I start off with this initial condition, I write out its binary equivalent. So this is 0.1, that means it's greater than a half, and so on. And once I iterate it, well, I'm just think of the arithmetic. I'm now just multiplying this times 2. So I take some fraction of the digits and I just shift it up by 1. It's pretty simple here in base 2. When we have multiplying base factor of 2, it just shifts everything up, right? So if I shifted 0.110, that would be 1.101, but then I mod 2, so I set that upper digit to 0 to put it back on the interval. And really what's happening is the picture here for the shift map is I take some window of bits, and when I multiply by 2, I just shift them up in precision. It just moves up. Just goes from here, shifts up here.
In some encryption, people use these things called linear feedback shift registers.
Yes.
Can this technique be used to actually kind of reverse engineer those types of things?
Yes. And some of those linear feedback shift registers are discrete maps on the interval or maybe the square. Kind of depends how much state information they have built into them. Absolutely right. So there's an interesting kind of what you might think of as a dynamical systems analysis of random number generators. And many, many, many of them are various kinds of shift map. Those tend to be terrible random number generators, it turns out. They're very crackable if you wanted to use them. That's kind of would be a fun project to kind of take this dynamical system analysis and look at crypto systems and how what makes for a good non-crackable code and that kind of thing. Good random number generator. Yeah, here it's just trivial. If you know the lower bits, I know what's going to happen next. So in that sense, it's predictable. However, let's think about this physically. I mean, this system is going to be predictable if I know x0 to arbitrary precision. In any experimental system, just like in our dot spreading experiments, there's some fuzz, right? And wherever that fuzz is, what happens in the shift map is that it just marches up until that's all you're seeing. Or, as you'll see, I think in one of the labs, if you do the shift map or the Baker's map or the dissipated Baker's map and friends on a digital computer with finite precision, even though it has floating point, it has finite resolution. IEEE floating point's a 64-bit format with 54 bits of mantissa, the fractional part. And lo and behold, as you iterate this, whatever, you can start with your approximation of 1 over pi is x0. After, kind of depends on a few little things, either 53 or 54 iterations, you're looking at the round off, which is deterministic, and the shift map on an IEEE arithmetic computer goes to 0 after 53, 54 iterates. So this is a way of checking your precision, if you wanted to see. If you didn't know, I mean, sometimes you're using Python or Perl, and you want to know, is it C, C++? Is it using IEEE 80-bit or 64-bit? This is one way to check it. Just shift. But it's just shifting, so this is not a surprise. So there's kind of there's a view of these chaotic systems that all they're doing is excavating all the bits down at the least precision end of the arithmetic representation, or down at the heat bath level. Turns out that's too simple a view, but that's not a bad first cut, and that's certainly the dynamic that the shift map embodies. Just excavation, just shifting up the bits from lower precision bits.
Can you get to this map? I think I remember it's some sort of transformation from the logistic
Yes,
map,
right.
The article
Right. Well, I'll probably even mention that today. Yes. Right. What you're talking about, it's not an unusual technique to, since this is so well understood, I mean, the mechanism is kind of trivial. Once you see it, it's kind of trivial what's going on here, right? mean, independent of, oh, it's stretching and kneading state space. No, it's just shifting up the bits in this simple case. Therefore, if you can find coordinate transformations from what appear to be more complicated dynamical systems down to this, then it's a huge win there. Yeah. So, and this happens, this is done all the time as a kind of analysis. Okay, so what I want to do here is get back to the Lyapunov exponents. So this will be a more explicit discussion of Lyapunov exponents for one-dimensional maps. One-dimensional dynamical system, we have a single Lyapunov exponent. Okay. And the basic picture is kind of zoom in here, kind of one-dimensional map setting, state space goes to itself, and we're going to have some initial point and look at the evolution of some small deviation delta zero. And then that turns into, well, of course, f of x, and then f of x plus delta zero, call that difference delta one. And we keep doing that. So the picture we have is, this is like writing down the local linear flow we did way back when. We had some discrete time system like this. What determines the growth of the size of these small deviations is just the slope at the point. So the slope at x0 increases delta 0 to delta 1. The slope at x1 increases delta 1 to delta 2, and so on. So we, again, make this picture that if we started with some small separation delta 0, there'll be an exponential growth of that as a function of iteration controlled by some rate, lambda. Or we turn it around, take logs of both sides, pull the lambda out, and we define the Lyapunov exponent in one dimension this way. Again, very similar motivation to the general flow case. We just look at how this separation delta n grows, and then look at the ratio. Take the absolute values because we're only interested in the magnitude of the stretching or shrinking. Take the log of that, so it's an exponential rate, and then do a time average or iteration over steps, iteration steps. And that'll be the Lyapunov exponent for 1D. Now, it turns out, and here we have f. So there's some more we can do to simplify the definition, and it gives us a very handy algorithm for calculating efficiently the Lyapunov exponent. So what I can do is just substitute in the expression for delta n. Like I said before, it's going to be the difference between f to the n of x plus delta minus f to the n of x over the initial separation, which was just delta 0. Well, that should look like your basic calculus epsilon delta kind of argument for a slope of the derivative of f to the n as delta goes to 0 here, right? Okay, well, that's good. So what we're doing here is we just start at some initial condition, and then we look at high powers of this function, then take its derivative. Well, that can be kind of unwieldy. So there's a simplification here. Chain rule. So if I have the derivative of some power of a function, that's the same thing as the function's derivative at the series of iterated points. Or the other way to say it most clearly, the slope at x0 of f to the n is simply the slopes at the successive states, x0, x1, x2. And we just take the product of that. So simple calculus move. Then substituting that in here, we end up with this simple definition. So this is what you would compute with. Again, and this is not hard, right? Logistic map, shift map, these are all like 2 lines of code. And this adds another line of code, or maybe 2. So time average of the sum, right? What I've done here is I have the log now. I just argued that log of what's in here, that's a product. Log of a product is a sum. So I get a sum of just the log of the slope, absolute value of the slope, at each point along the iterate. This is algorithmic, right? x0, get the slope, record that. x1, take the slope there, and then you just multiply these. Then you just add up the logs of those slopes and average over the trajectory you've calculated. So pretty simple. Same criteria here. When it's negative, we'll have a stable fixed point in 1D. That's all we have. And then positive will have some degree of instability or chaos. Okay. Let's do a couple examples. Hopefully almost anticipate what's going to happen here for the shift map, right? Everywhere. Our little delta 0, our little variation is going to be multiplied by 2. Everywhere, independent of where we are. So that's easy. It means that this argument doesn't depend on x, and in fact, it's just a constant. So we end up with f prime everywhere is 2. Plug in 2 with log of base 2 of 2, well, that's just 1, and we end up with the shift map having a Lyapunov exponent of 1. If you like units, since I used log 2, anticipating our information theory, the units would be sort of loss of bits of resolution per step. So bits per step. So that was easy. How about something a little less trivial? So here's the tent map. It's also a map of the interval to itself. I've drawn here in green just a kind of typical setting for the control parameter A. And you can see why it's called the tent map. I have these 2 monotone pieces, but now unlike the shift map, above a half, it has negative slope. The map has negative slope. And here's the functional form of that. The slope here is written out as A, and it goes between 0 and 2, 0 and 2. And the maximum, the height here at a half, at the maximum, is A over 2. When A is equal to 2, the map goes all the way to the top at a half and comes back down. And we can also look at a bifurcation diagram for that. So here is A going from a half up to A equal 2, where it goes all the way to the top of the interval. There's nothing much interesting going on when A is less than 1, because the map is always below the identity for A less than 1. A over 2 is the height, so it doesn't get above a half. And then something interesting and bizarre happens at A equal 1. There's this very dense, you'd actually have to zoom in here, behavior suddenly. So a little bit unstable. It's maybe easier to understand. At larger A, we end up with, in fact, it's almost impossible to see here. They're so small, but actually it's like pure band merging. We have these little bands. Here you can see it's sort of the larger scale. Here there are 2 bands that merge, and then we just have 1 band up at A equal 2. But actually right around here, you can almost see, you'll see it in the slides if you look closely, there are 4 bands merging to 2 bands, and down here's 8 bands going to 4 bands and so on. But it's all greatly shrunk down. It's kind of degenerate, and then they all kind of collapse on a half here. So anyway, we don't have any of those periodic windows that we saw for the logistic map. It's just pure chaos the whole way up. All we have are these band mergings. So a little stability analysis first. This is the sort of required boring work to do. Well, the map here is shown in gray. The first iterative of the map always intersects the origin at 0. So we have this trivial fixed point for A between 0 and 1. As soon as A goes above 1, I've kind of drawn a typical second iterative of the map here. In green, it crosses the identity in, well, the original fixed point of the map. So there's a single fixed point here. That's the non-trivial fixed point. And then we have also period 2 orbit. But just like before with the shift map, since we know what the slope is, A or minus A, as soon as A is greater than 1, wherever the map crosses the identity, we have fixed points or periodic orbits. And since the slope there is greater than 1, A, they'll be unstable. So same argument, just like for the shift map. The tent map has a countable infinity of periodic orbits built into it, and they're all unstable. Let's calculate the tent map's Lyapunov exponent. So here's the formula again. So what we need to do here is calculate along an orbit the slopes at the points, f prime at the points. Well, we know that the map either has slope A or minus A, wherever it is. We don't know exactly when and where, but it doesn't really matter. We just have plus or minus A is the slope, but we're taking the absolute value. So this all falls apart, and the claim is that the Lyapunov exponent is simply log of A, the control parameter, or the slope. So that's easy. And here's what it looks like. So going from a half up to 1, it's negative. So this is just the stability of that trivial fixed point at the origin. Then at A equal 1, suddenly there's just a little bit of positive exponent, a little bit of instability. It just grows monotonically all the way up to. Finally, at A equal 2, it's like the shift map. It has a lambda of 1 bit per step. But here, closed form solution, nice. Provides some kind of base case for us. Although that would, it's our euphoria is somewhat limited when we step up to the logistic map. Okay, so the logistic map is different than the previous two because most basically the slope depends on where you are. Slope goes to 0 here, slope is very large here. So there's going to be some complicated mixture depending upon what the height is, and as we iterate the orbit, and we have slopes that are very large and there's separation, or then when the iterate value comes close to a half near the maximum, there'll be some contraction because the slope is going to 0. But that, of course, makes it fun. So just to remind you, here's the bifurcation diagram again. This is R going from 3 to 4. So if you remember, for R less than 3, there's just this non-trivial 1 minus 1 over R dependence on a period 1 fixed point that goes unstable here. I'm not showing it. Just keep things simple. And then we have this birth of a period 2 orbit, high, low, that goes unstable. It's still there, but it's now unstable. And then we have a stable period 4 orbit, period 8, period 16, and all the way in. Period doubles to the n. And then we get this sort of chaotic behavior with these now windows in here. The windows are due specifically to the fact that there will be orbits that visit a half arbitrarily closely, which means they'll pick up that stabilizing effect of the slope going to 0, that's shrinking perturbations. So what can we say? Well, there's still something to learn from all of this analytically, and we can use now the Lyapunov exponent to calculate the stability of the fixed points that we've seen. So again, the slope now depends on where you are. It goes to 0 to half. So if we start out with our formula, what we're having to calculate here, and typically you do this, except for the cases we'll cover, in the general case, you do it numerically. So just averaging, time average is log base 2 of the absolute value of R, 1 minus 2x. So we have our trivial fixed point at the origin. That's stable for R between 0 and 1. The slope there is just R at the origin. Therefore, through that whole range, the Lyapunov exponent is log of R. Notice that when R is 0, this diverges negatively. And that's actually a little signature that we'll see elsewhere. The non-trivial period 1 orbit is 1 minus 1 over R. That was stable between 1 and 3. And we calculated in the previous lecture that the slope was 2 minus R. Notice that this goes to 0 in the middle of the range, right? So before we decided that this non-trivial fixed point was stable between R between 1 and 3, well, R equal to 2, this diverges negatively. It's extremely stable. It's called, at that value, it's called a superstable period 2 orbit. And that's this definition here. So whenever you have an orbit that visits a half, or wherever the slope goes to 0, half in the case of logistic map, then the Lyapunov exponent is going to be dominated by that. The system will be arbitrarily stable. Now, there are two other conditions where we can say something about the Lyapunov exponent. Wherever we have a bifurcation, in other words, we're going from period 1 to period 2 to period 4, we have to give up stability of the previous behavior to take on a qualitatively different kind of attractor. So Lyapunov exponent has to go to 0 there. And also, it's kind of a corollary of this, right at the onset of chaos. After all those period doublings, lambda also has to go to 0. I'll show you a plot of that in just a second. A little bit of an aside. In the case of one-dimensional maps and simple multi-dimensional discrete time maps, there are other ways of calculating the Lyapunov exponent. So this is a little bit kind of presaging our discussion of the origins of probabilistic behavior in maps, which we'll start doing next week. So rather than do this time average, so this is what's called the ergodic theorem. It goes way back to Poincaré and Boltzmann and early mathematical physicists. The question was, do my time averages represent what's typical in the state space of the system? So we say that a system is ergodic when time averages and state space averages are the same. The way I introduced the Lyapunov exponent here, this was a time average. Here's some function of a trajectory. happens to be this particular one because we have the stability interpretation. Could be other functions like the average temperature, whatever, something like that. And I'm just sampling this and then averaging it over time. So now, is this typical if I were just to randomly observe points on the attracting invariant set? So that would be that's the notion of ergodicity. So in some cases, we actually know what the long-term distribution of the iterates is, curiously enough. Again, we'll come back to this and we'll spend a week talking about this concept, but just quickly, in the context of Lyapunov exponent. So just like we were talking about having attracting invariant sets, there's also a notion of an invariant distribution, right? An attracting invariant set is something that if you start there, the flow takes it to that. Here, the sort of invariant distribution is a distribution, a set of behaviors on the invariant set, and probability amplitudes such that when the map acts on it, it comes back to itself. So formally what I mean is somehow, and this takes a little bit of work, somehow I apply f to this distribution and it comes back to itself. And in a number of cases, you can actually solve this kind of formal equation here. We'll do it explicitly. You can solve this formal equation. So if I have this distribution of behaviors, I don't have to do a time average. I can just immediately calculate the Lyapunov exponent by just doing an average over the state space. I just do this one-dimensional integral, well, over the invariant set, or 1D map would be over the interval. I just average the function I'm interested in, log of the slopes, against the probability distribution. And that's also the Lyapunov exponent. So the two ways to do this. One is time average, which would be the way you do it, say, if you're simulating things, or if you have some prior knowledge of what this asymptotic invariant distribution is. And we'll go through and derive this P for the tent map and shift map and show you for like the logistic map. Just real quickly, it turns out, and it always kind of surprises me, that way back when the logistic map was first invented in the Manhattan Project in the 40s, they had just taken delivery of their first digital computers, and they wanted a way to generate random numbers to sample these very complicated integrals they needed to test the stability or instability of certain materials. And there's an early abstract published by John von Neumann, the mathematician. He just writes this down, was able to calculate out that for the logistic map, where r equals 4, so it goes all the way to the top of the interval, takes the whole interval up to itself, that this is the asymptotic invariant distribution. And in principle, you can just calculate the Lyapunov exponent by averaging the slope function, log of the absolute value of slope, against this distribution. Actually, the way you actually solve this is a coordinate transformation back to the shift map, because that has a nice simple invariant distribution which is constant on the interval. Anyway, the net result after all that kind of rigmarole calculation is that you find for the logistic map you have lambdas 1 bit per step. Very simple there. It turned out to be, like we were talking about before, a very bad random number generator. There are ways of breaking this. There's some structure and regularity in it, despite the fact that it seems to be pretty random. Okay, so all that said, the real state of affairs with the stability in the logistic map is shown in this plot of the Lyapunov exponent as a function of r, going from 3 to 4. And it looks much more complicated than the tent map, which is just log of the parameter. Here we have, bifurcation is occurring here between the non-trivial period 1 to the period 2. And what we see, we go through lambda equals 0. And then right down here, somewhere around here, we have the period 2 orbit crosses a half. So that point on the orbit is visiting the 0 slope region of the function. Therefore, it's arbitrarily stable, and Lyapunov exponent goes to minus infinity. So that's super stable period 2. And then above that, it's less and less stable till we come up to where period 2 goes to period 4, and it happens all again with a super stable in between, and so on. So the period doubling is kind of easy to see here in the Lyapunov exponent with these super stable, kind of organized by these super stable negative spikes. Then this all eventually accumulates right around r equals 3.569945, right around here, after all the 2 to the n doublings. And then we see our first positive exponent. And then that just gradually grows until we get all the way up to r equal 4, which von Neumann told us had a Lyapunov exponent of 1. So numerical verification of his analytic calculation. Now, obviously, there's a bunch of other stuff going on in here. So For example, this big divot here, this big negative thing, that's the period 3 window. And there's a super stable period 3 orbit down here right around 3.83. It actually goes through period doubling again. It looks a little bit ratty here because I only took a discrete set of R values when I was calculating this. So you're not seeing all the details. But every other one of these spikes here is another periodic window. I just happen to be choosing some R value where, oh, it's period 17. And again, in each little window, there'll be period 17 goes to period 34, goes to period 68. The whole thing happens again, little band mergings until it joins the main sequence. You can also see there's kind of a signature here where 2 bands merge to 1. Or even here, where just as R goes up to 4, there's this kind of quick, steep rise in lambda until it fills out the full interval. Same thing down here where 2 bands go to 1 band. There's a steep rise and then a kind of a plateau afterwards. There's also, in fact, it's right here. That's 4 bands going to 2 bands, and you can't quite see it because there's not the resolution and so on. So there are things that we've seen before, and there's a signature as a function of R in the Lyapunov exponent. So there's a lot of information in that. And these various points that we can analyze in some detail, whether it's super stable periodic orbits, where the bifurcations between periodic orbits occur, where these band mergings are, where these periodic windows are in the middle of this chaotic background. We just look for the super stable period 3 orbit, super stable period 5 orbit, and those are kind of the organizing centers, so the ways of calculating the parameter values where those things occur. So there's a lot. Now it's turns out there's an interesting result where if you pick any value, any R value up in the quote chaotic regime, it's an arbitrary one, and if you can show that it's actually has positive Lyapunov exponent, it's chaotic, there is an arbitrarily small perturbation away from that will lead you to periodic behavior. Now it might be period 1,032,000, but there it is. So this plot I'm making here is just a little sampling into what is essentially a non-differentiable function. Lambda as a function of R. It's extremely complicated. So kind of harkening back a little bit to when I first started talking about bifurcation theory, we're sort of this picture of I'm varying a parameter, there's this one-dimensional arc going through the state space, and how is this arc punctuated by bifurcations? Well, here's a picture, arbitrarily complicated. Small variations in the parameter can lead to very different, qualitatively different kinds of behavior, going from chaos to periodic behavior and back again. So you might, throw up your hands in despair, although this kind of complication entertains some of us. But there's quite a bit we understand about that overall bifurcation diagram. And this is one of the sort of more elegant connections between statistical physics and nonlinear dynamics, trying to understand the structure of these bifurcations along the period doubling route to chaos. So let me start with just the kind of superficial view. I don't mean non-trivial, I mean from a distance. So here's this original bifurcation diagram. The interval and how the attractors change in R going from 3 to 4. And what I'm going to do is pick a square here and then blow it up. So I've taken this red-orange square here and I blow it up to the same aspect ratio as the previous full diagram. And then what you see is something that looks kind of similar. Notice the parameter range is much smaller. So instead of 3 to 4, R goes from 3.449 to 3.679, very small window. And I've also blown up, zoomed in on the state space. So instead of going from 0 to 1, X goes from 0.27 to 0.727. But, you can kind of convince yourself that this bifurcation diagram kind of looks like the whole thing, although it's upside down. Well, let me just do this again. I'm going to pick this square here. And what I'm doing when I pick these squares, I'm actually picking the sort of sub-bifurcation diagram that contains a half. So I'm kind of zooming in around X equal a half as I do this. And then I blow it up again, and then lo and behold, now this thing looks almost identical to this, even in terms of the orientation. So we had period 3 window, period 5 window, band mergings, all that. Period 3 window, period 5 window, band mergings, everything else repeated. But now I'm looking down at between 0.41 and 0.59 in the state space in X, and then between 3.544 and 3.593. So this diagram here, just to drive the point home in purple, is that little square up there. So what that means is that this, what seemed to be a very complicated set of behaviors along this parameter arc actually has quite a bit of structure. In fact, it's self-similar. It itself is like a fractal in state space cross parameter space. And we can use that to say some more quantitative things about how this period doubling bifurcation sequence and how the band mergings are organized. So this was done, this theory I'm going to talk about, and I'll give just a very quick overview of it, was introduced in the late 70s by particle theorist Mitch Feigenbaum, using some ideas from the theory of phase transition of critical phenomena called renormalization group. I won't go into the details, but give you kind of an overview of how that theory goes and also what it predicts. So people had known for some time, actually going back to the 60s, since this logistic map is so easy to calculate, and it had been introduced at Los Alamos during the Manhattan Project as a random number generator. People had been playing around with this. In fact, there was a large amount of work done in the 40s, 50s, and 60s. It was classified because it had originally been introduced in the context of making the atomic bomb. So there was a lot of this work on nonlinear systems that wasn't actually declassified until the late 70s. Mitch Feigenbaum was a postdoc at Los Alamos and talked to the mathematicians who had done this earlier work, and then that's how he came to develop the scaling theory for period doubling. Okay, so what is the phenomenon here? How are we going to look at this? So here's our original bifurcation diagram, and what we're going to do here is think about the periodic orbits, period 2, period 4, period 8, and just focus on their superstable parameter value. And it's kind of comparable across these different bifurcations. So we have period 2, period 4, period 8. And then what I'm doing here is I'm interested in the spatial rescaling as a first question. So here I am at the R value where I get period 2 superstable. And I'm just going to look at the distance. How wide is that period 2 oscillation? And I'm going to compare that to the period 4 superstable parameter value, and then how separated that fork is, and I'll compare that to the period 8 superstable and how wide that fork is. And then the question is, do these D values, D1, D2, D3, how are they related? Is there any systematic dependence on these things? As I'm varying my kind of stage in the period doubling. Period 8, period 16, period 32. I go all the way down, kind of zooming in on this onset of chaos value R. Well, and it was noticed early on, partly by Mitch using an HP hand calculator, that if he just went and calculated this, it's a one-dimensional map. This is the benefit of lowering the dimension. You can actually do it by hand. That you empirically look at these distances and you compare the sort of previous value, the change in, I was talking about alpha here. So what I'm doing is I'm just going to look at the previous value versus the next separation. So D1 versus D2, D0 versus D1. And if he did enough of these, he noticed that the lengths, actually even included the direction, was minus 0.25. The minus means that this direction flips each time. And then this distance is now 2.5 times larger than this, which is 2.5 times larger than that, and so on, all the way down. And you can do this if you start to use some arbitrary precision arithmetic. You do this quite accurately. The other question here is, how much do I have to change the R value to go from one superstable orbit to the next one, to go through period doubling? And then the ratio of these intervals in R, delta R1, delta R2, delta R3, that converges to about 4.7. So as I go to higher and higher periodic orbits, the separation between the orbits goes down by about 2.5, and they sort of pile up geometrically fast as I go towards the onset of chaos. The amount I have to go from period 32 to period 64 is 4.7 smaller than I had to go from 16 to 32. So it gets very, very delicate in here. They all kind of pile up. All the period doublings pile up around here, geometrically fast at that rate. So that was kind of the empirical description of this self-similarity. And the whole time what we're doing is here's in green I have x equal 1/2, that's the maximum. So I'm kind of focusing in on just the region of the state space around 1/2. So the question is, how do you describe this? So this is this notion of renormalization group. The idea is that in the limit, as you go towards the onset of chaos, there's some regular thing happening. So how are we going to describe this? So the two things that are going on, I'm changing the parameter value, and then I look at a smaller region of state space. So I'm trading off changing the parameter value to how much I magnify and look at this, the state space. So if this, so imagine I have, I set the parameter value to the first superstable period 2. I have some function, color that green, okay? And then what I'm going to do is change to the next parameter value in the sequence to get the next superstable orbit. And then, since the period is doubled on that, I look at f squared, and f squared generically looks like this. But the idea is I want to zoom in on this little hump here and then blow it up in x and then flip it over in the range and compare it back to this original. That's the statement of, after we did our blow-ups, I then said, oh, it's just like the original thing. So the idea is that as I go through this series of parameter values, I look at higher and higher powers of the function, but then focus in just around a half. And the idea is that what I'm seeing locally here should be like the whole map I saw before. So the spatial rescaling is that alpha parameter here in the range and in the domain. That minus sign for alpha means under one thing, under one change in parameter value, the map flips over. If I did it again, it would flip back. Okay, so how are we going to describe, okay, enough of the geometry. What about the mathematics? The idea is around a half at some parameter setting, superstable parameter setting, it looks like the map f squared around the next superstable parameter value, but rescaled in domain and range. So that's what I just said before when I was waving my hands. This is the idea, that somehow the original map looks like f squared, but zoomed in and flipped over. Yeah.
So does the alpha, I mean, the range and domain scaling has to be the same scale?
Yes, yes. Well, have to, it didn't have to, I guess, but yes, it is, yeah. Yeah. And then so on. The idea is, kind of argued by the series of bifurcation diagram zooms, the idea is this keeps going further and further into the period doubling sequence as we get close to the onset of chaos, so that eventually we're looking at powers of 2 to the n of f, focusing around a half, rescaling by some appropriate n-dependent value at the nth superstable orbit, and that should look like the original function. So, I mean, there's squiggly signs here. It's just kind of qualitative. So the real jump is asking if, in the limited infinite period doubling, this thing actually converges to a function. At least it's well behaved around a half. We call that g of x. And the idea is that this would be universal. But that terminology comes out of phase transition theory. The idea is that it really doesn't matter what f looks like except right around a half near the maximum of the map. All the other variations are sort of falling away. So even if you use the sine of x map or cosine of x, those are different explicit functions. If you get far enough into the period doubling, they should all look the same and scale the same way. It might take them a while to get started up to have the right 4.699 parameter rescaling or minus 2.5 spatial rescaling, but once you get close enough to the onset of chaos, the end of period doubling, then this G should exist. So, or the other way is say is right at the onset of chaos, so now I'm kind of moving up in the bifurcation, right there, right at the very end of the period doubling, that this should look like itself, the function should look like itself at the same parameter value, but rescaled in domain and range, and then the square of the function. The net result is, again, it's an assumption, such a thing exists. So that turns into this question, specific question. Is there a G such that when it's squared, rescaled in the domain and its range, it comes back to itself? We don't know, but there it is. And we have this relationship between G and G squared, but does it exist? So this is a functional equation, and you have to put some boundary conditions on it. We actually sort of shift the origin from x equal half to 0. It's just easier for the calculations you have to do. And then, of course, this function at this new value, shifted maximum value has zero slope. Now this gets kind of messy. I mean, the goal here is, can I somehow, with this constraint, find such a G? Well, that's what Feigenbaum did. And basically what you do is you roll up your sleeves, or you go talk to Mathematica, but he didn't have Mathematica back then, and you just do a power series expansion up to, turned out to be 4th order, actually 6th order. You can show the function has to be even, so you can drop odd powers. And then you plug this back in, and then you identify the coefficients of the similar powers of x. I've got a worksheet somewhere, which if I clean it up, I'll post it up on Sage, that does this, using the symbolic manipulation part of this. And then from this, once you do this, you can actually write, well, you can solve for the coefficients and actually solve for alpha. And lo and behold, it comes out to be what was measured empirically. So very nice piece of work. There's a fair amount more work to do if you want to calculate this parameter rescaling value, delta, 4.7. Similar kind of calculation, expanding to some order. So again, we didn't go through the calculation here. Strogatz does a little more in-depth sort of stepping through the calculation. There's some, you can do it to 2nd order. It doesn't take too long to do that by hand. So now, why do we care about this? Well, one of the important roles, in addition to taking ideas from high energy physics and phase transition theory and bringing them into dynamical systems, it's kind of amazing. You can think now that chaos appears through a phase transition. So there's some analogies that became very powerful in doing further analysis. That as I'm controlling the parameter in the logistic map, that the way chaos comes about is through a phase transition. Because this renormalization group predicts certain scaling values. And the important thing is, when we went to look at turbulent fluids, this is a prediction. The idea was, oh, turbulent fluids, whatever dimension they're in, they might go through period doubling, and if they do, and there really is a kind of dynamical system description of what they're doing, then you should be able to recover from the experimental data these scaling exponents. And so that was done in the early 80s. So it's like one of the first rather general predictions about how chaos appears. The competing theory in hydrodynamics was due to Landau, and his theory was that what happens is that you build up more and more incommensurate oscillations, or in our language, that you go from a limit cycle to a torus, to a 3 torus, to a 4 torus. And in fact, at least for the kind of flows where this was discovered, this is a different mechanism. It goes through period doubling, doesn't go through quasi-periodic behaviors to become chaotic. So that's it. So I just wanted to show you that I'm kind of oscillating around saying, oh, these things are impossible to solve. Well, I showed you a closed form solution, but there were some gotchas with the shift map about chaos and having to think about precision. There's actually a very interesting subset of the work in dynamical systems that looks at different maps as sort of arithmetic encoders and different kind of forming their own bases, arithmetic bases, that keys off of this notion of an initial condition you write down in some basis, like base 10 or base 2, and see how the map excavates digits. Interesting work in coding theory based on that. But the main idea here was just to show you that there's some non-trivial behaviors, not only in terms of chaotic behavior and how we measure stability and instability, but also in terms of bifurcation structure. So that's it for today. Any questions? So how are the homeworks going? Are we struggling? So things are starting up slowly. So I'm going to start going through, and the goal is the end of next week to bring everyone up to speed, including the Berkeley folks who started late, so that we're all synchronized. I'm debating now about the next couple lectures, what to include, in particular, maybe as part of slowing down on the homeworks and giving us a little more time to do a couple lectures that are about spatially extended dynamical systems and how some of these ideas work, where you have dynamical systems coupled together in arrays. So we can think about, those are in principle infinite lattices, therefore infinite state systems, but there's a lot you can say because the local dynamical systems are coupled together. So there's some spin systems and cellular automata and lattices of logistic maps we could study, but kind of qualitatively, just to give you some sense of that the general qualitative dynamics framework still applies in that case.